look at a couple of the details that we want to cover on the acquisition tab, and then as we go through our example, hopefully we'll cover these points. First, the full spectrum. We want to point out fewer channels yielding a faster response, talk a little bit about when to use averaging and some of the memory and time constants considerations for full spectrum averaging, as well as some details on setting up gains to avoid saturation, using gains and thresholds, and then also, since we're looking at a dynamic interrogator, to explain the concept of peak tracking as well. So first, we've just connected our optical sensors to our instrument, or they were already connected to our instrument, and we launched the application. So a few things here are immediately apparent. We have some very abnormal-looking sensor shapes. If we look down at the level, we see a level of 0 here, and that's where we would expect our noise floor to be. So we're seeing quite a bit of signal below that 0 level. And if we zoom in to any one of these sensors, we can see some very abnormal sensor shapes. So I'm going to zoom back out to our first point. If we're displaying all 4 of our channels in full spectrum, it takes time for the ENLIGHT application to update all 4 of those graphs. There are, how many data points are those, Dan?
32,000.
Some 32,000 on 4 channels. And so there's a degree of processing there. If we want to speed up our data display to do some diagnosis, we can turn off the channels that we're not interested in, and then we're going to get a much faster response. I'm not sure if that comes across the WebEx demonstration or not, but here we get a much more dynamic and live response. So with that view, let's zoom in on one of these sensors. And the first thing that is apparent here is this does not look like a standard optical sensor spectrum. So we immediately conclude that there must be something wrong with either our thresholds, our gain, something of the peak detection. And in particular, the issue with this sensor is that it's in deep saturation. So that means that our gains are set particularly high for the reflectivity of this sensor. For this demonstration, we've actually set the internal gains of our instrument very high so that we ensured that we would start out in this condition. Typically, what you will see is for a 90% reflectivity grading at a gain setting, here we are on channel 4 of 0, that it should come out to a level of about 3,000 counts, leaving you with a good signal-to-noise ratio and no saturation. However, if the gains are set higher than 0, then very frequently you may see a situation where the sensors are saturated. And so the way we're going to go about addressing that saturation in our setup is by adjusting the gain. Also note that on the application, in the user interface, that the gain controls here match the channel controls and the display in terms of color. So here channel 4 is in green, the graph is in green, and these controls are in green. Okay, so here I'm going to adjust the gain down. And I went from 0 dB to minus 2 dB, and we see that it's beginning to resemble minus 3, minus 4, minus 5, minus 6. Okay, now we see we actually have what we would consider to be a more traditional sensor shape. And so with this, we can see the peak of the sensor, and it's below 4,000 counts, which is our critical point for saturation. So now this sensor is unsaturated with good signal-to-noise ratio, and so this is a sensor from which we can derive good strain and temperature information.
Please note the dashed line at the top of the peak. What that is indicating is that the instrument is detecting the peak. You have to make a little bit of a difference between ENLIGHT sensors and the detection on the instrument. So by seeing that dashed line, we're confident that the instrument itself is now detecting that peak.
So if we zoom back out, we can see that we have our gain set well for the first sensor, but we're still saturated on the second sensor. Again, a quick indication of saturation is that you will see a large proportion of that power reaching all the way down to the bottom of the display. And so I'm going to continue reducing the gain here. And now we can see we have dashed lines on both of our peaks, and that they are within the range that we want for good SNR and lack of saturation. So it should be noted that for this demonstration, we've turned up the gains very, very high on our demonstration instrument, requiring that we reduce the gain to a large negative value. Typically, this would not be the case, but you should also be aware that should some situation arise, we have a very highly reflective peak, and perhaps there was a slight change in laser output power, the negative gains are available to compensate for that type of a situation. Okay, so I'm going to toggle back here. We've done the full spectrum, adjusting gains. So note that, that on the background of our channel 4, as opposed to channel 3, channel 2, and channel 1, that our gain is now labeled with an uncalibrated parenthetical reference, and that the background is turned yellow. During calibration, all of the instruments are calibrated from a negative gain of -5 up to a positive gain of 20. And so if a negative gain beyond -5 is required, ENLIGHT will still facilitate that, but the exact translation of how many dB per adjustment is uncalibrated below -5.
However, it's really more of just for the ability to track that with dB. It doesn't affect the performance of the instrument or of ENLIGHT in any way. Okay, so now we'll turn on some additional channels. And here I've turned on channel 3, which is where we're going to connect our first chain of fibers. If you remember back from our bridge graphic, we had one fiber that had multiple strain and temperature sensors on it, and that's what we're going to connect to channel 3 and demonstrate some of the other features of the acquisition tab. Okay? Again, we note that we're in a deep saturation here on these sensors, so I'm going to adjust the gain down until we no longer are. Okay? And so I'm going to turn off channel 4 here so we can focus exclusively on channel 3. Okay, we can see in the purple diagram that we have 5 spectral peaks, or we have 5 features that resemble peaks. But when we look down underneath the channel 3 acquisition controls, we see that there's a number of 5 peaks, but that it's got a light red background. So this indicates that the number of peaks that the SM130 had been detecting and expects to detect has changed. And that makes sense because we've now inserted this fiber and connected the fiber to the interrogator. So there is a communication that's established between ENLIGHT and the dynamic interrogator to contend with either sensors dropping out or sensors spurious peaks coming in and disrupting the order in which sensors are detected. And so we're going to go through a little demonstration here of this peak tracking communication between the instrument and the application and how that's used. Okay, so essentially, the ENLIGHT application and the SM130 had established when they first made a connection that there were 0 spectral peaks on channel 3. Now we've changed that situation proactively, and so we need to go and tell the application to resynchronize those peaks or to reset wavelength tracking. And I've highlighted that control down here on the bottom left. I'd like to point out that in 3 separate ways, ENLIGHT is telling you that there's a problem between the acquisition and what the number of peaks that are expected. As Todd pointed out, below the channel parameters, the count of 5 is background in red. Also, if you look at where the mouse is now over the peak tracking button, the small target symbol has turned to red. Normally it's blue. In addition, on the top left of the acquisitions tab, you'll see there's a red exclamation point. And that's useful if, say, your system is up and running and you're on a different tab. By seeing the red exclamation point, you know to come to the acquisitions tab to find out what is wrong with the system.
Additionally, that information has been logged into the event log under the alerts tab. And you'll see at this particular time, at 9:22, we have a warning on the instrument that there's been a wavelength tracking fault on channel 3. In other words, the SM130 and ENLIGHT were expecting there to be 0 peaks on channel 3, and now the SM130 is detecting not 0 peaks. And if we go back to the acquisition tab, we can see that it's detecting 5.
And at the end of the presentation, when we show the log file that we turned on just a little while ago, you'll see that that is saved into the file. And by setting that to save to the disk, we can come back at any time, even if our system was to reboot or reset, and know what had happened during the time that the system was operational. One other thing I'd like to point out is the reason why peak tracking is so important is if you've used an SM130 without ENLIGHT, you know that a lot of what's done in the dynamic interrogator is done internally. So the averaging, a lot of the distance compensation are parameters that are done internal to the instrument, and the instrument has a set of indexes that it uses to apply to these settings to. So without peak tracking, if you had 3 peaks and one of them disappeared, say number 2, then all of your averaging, distance compensation, and other quantities would be applied incorrectly to the remaining peaks, and all peaks above the failing peak would be inaccurately reported.
So let's demonstrate that feature in action. We're going to click on the reset wavelengths tracking, and a couple things will happen. First, the background goes from this light red to a gray, and you'll also notice that we have dashed lines on all 5 of those sensors. And so now ENLIGHT and the SM130 are in agreement and synchronized on how many spectral peaks are supposed to be detected. I'm going to move over to the table view quickly and look at channel 3. Now we have these sensors at 1531, 34, 1541, 46, and 1553. So let's go back to the graph and demonstrate why that spectral tracking is important. So we can do that either through an attenuation of the fiber, changing of the gain, or I'm just going to change the detection threshold for channel 3 and increase that. So as I change that threshold, you see the dashed line, which is the effective threshold, increase. Okay, and now at 1,000 counts, you'll notice that the 2 center peaks have fallen below our threshold and are no longer detected by the instrument. So again, we have a wavelength tracking fault. The interrogator is only detecting 3, but reports or indicates by our 3 red indicators that it was expecting a number other than 3. Additionally, we see a dashed vertical line where the last location in which ENLIGHT was aware that these spectral peaks were reported. As Dan explained a minute ago, all of the internal distance compensation and averaging, or all of those processes, are done inside the interrogator, so it's very important that, that the application remains synchronized. So now if we go over and look at the table, we note that even though only 3 peaks are detected, both ENLIGHT and the SM130 are aware that there were 2 additional peaks that we're expecting to receive, so that the remainder of our data processing chain will continue undisrupted, and there won't be a wholesale shift of this 1553 peak down to the position of peak sensor 3. And that'll be very important as we establish our sensors in the next tab.
One application where I've seen this is important is where a series of strain gauges undergo a large deflection, and as the peaks, as the strain increases, the peaks move, and as they move, they were decreasing. So during the life of the system, you would see these peaks decrease below the point of the threshold, and thus create this type of scenario in a real-world application.
And so in that real-world application, there would really be 3 options that the user would have to rectify it. First is probably the most unfortunate, is to just conclude that those sensors are no longer of adequate quality and that they're not going to be able to be included in the system. And so with the peak tracking on, then basically the remainder of the sensors can continue on as they were. If it's just a reduction in the amplitude, then the user can either change the threshold level or adjust the gains, or a combination of the 2, in order to recover those sensors as part of their acquisition system. And so that's what we're going to do here, is restore our threshold to where it was at 200, and you'll see that our number of peaks goes back up to the expected 5, and they are reintroduced into the table for further processing on the subsequent tab. Okay, so back to our outline. I think that takes care of what we were looking to cover in the acquisition tab. Again, there are some written detailed explanations of these features in the user manual at the annotated sections and pages.